next example is in your textbook. I just wanted to quickly go over it though. So let's take a quick look at it. So this is a trig function, and I'm just going to look at it following the same steps as before. We want to graph this function, but on a limited interval, right? So the first thing we're going to do is find the intervals for which the function is increasing, and we take the derivative, and then we try to find the critical numbers. So we set the derivative equal to 0, and we find that in this interval, these are the values where cosine of x is equal to 1. Okay, and then we need to test the sign of the derivative around 2 pi, really. And we find that the derivative is always positive, so this function is always increasing. We record our results down here, and here are the tests that I did. I tested f prime of pi and f prime of 3 pi, and the derivative is always positive. So by the decreasing test, f is increasing on the whole interval. Okay, so so you can tell right off the bat for step B that, you know, if you try to look for the local maxes and mins, you're not going to have any. The function is always increasing. Okay, then the next part of this example, we try to find the inflection points. So I've got to take the second derivative, and then we try to find where this is equal to 0, or where it's always defined. So we try to find where it's equal to 0. And we find that it's equal to 0 at these values. So we're going to test the second derivative between these values to see if it switched from positive to negative. Doing that results in this sign chart. And we find that in this interval it's concave up, concave down, concave up, concave down. So we fill this all in to make the graph. Before we do that, we find the full coordinates of the inflection points, and to get the inflection points, we're just going to plug these values, pi, 2 pi, and 3 pi, into the original function, and we get these as our inflection points, pi, pi, 2 pi, 2 pi, and 3 pi, 3 pi. So those are plugged into f. Now I go over here and I look at I'm going to sketch the graph, and what I did this time is, because I didn't have any local maxes or mins, I plotted the inflection points. And I also plotted the value of the function at 0 and at 4 pi. I knew from part A that the function was always increasing and that it passed through these 4 points. And then I just added the concavity. So concave up, concave down, concave up, concave down. And that's pretty much it. But this example is in your book, so you can look at that too. Okay, there's one last thing I wanted to do. On the homework, on the handwritten part of this homework, there's some algebra that, you know, some people might get tripped up on, so I just wanted to talk a little bit about solving equations that have radicals and also have, you know, variables occurring in the denominator. So here's the example that comes up in, I think it's part D of the handwritten homework. You have a function that looks like this, and you need to find the critical numbers. So you take the derivative, and you get 10/3 x to the negative 1/3 minus 10/3 x to the 2/3. So this is, you know, the function we have. So this is 10/3 x to the 1/3 minus 10/3 x to the 2/3. And you might be wondering, well, how do I, you know, solve for 0? And how do I solve the equation, the following equation? So what I'm going to do is, I already know that x equals 0 is a critical number because the derivative is not defined there. And yet at the same time, that is in the domain of the original function. So I'm going to pretend x is not equal to 0, and I'm going to multiply both sides of the equation by the greatest common denominator. Okay. The least common denominator. So in this case, that's 3x to the 1/3. So I'm just basically clearing out the fractions here. So let me write that down. And the only reason I can do this is because I've asserted that x is not 0, right? So when I multiply both sides in trying to clear the fractions, I end up with 10 minus, now this times this, the 3's clear, and then I have 10 times x to the 1/3 times x to the 2/3, which just gives me x, and over here I have 0. So this turned into a really nice linear equation, 10 equal 10x, so x is equal to 1. Okay, so now I know that the critical numbers are 1 and 0. Okay, but then you have to find, when you study this function for concavity, you end up having to take another derivative, okay? In this case, so here was the first derivative, okay, right here. So I take the second derivative, I get negative 10/9 x to the negative 4/3 minus, let's see, 29 x to the negative 1/3. Okay, so the function I end up with, I'm just going to rewrite this, is negative 10 over 9x to the 4/3 minus 20 over 9x to the 1/3. And I need to figure out, if I want to find the critical numbers, where this is equal to 0. Okay, so I need to solve this equation. And like I said, there's lots of ways to do it, but I like to just do it by clearing out the fractions and treating it like a rational equation. So I'm going to multiply both sides by the least common denominator. So I have my left-hand side, and I multiply this okay, and then when I multiply this out, these cancel, and I end up with negative 10 minus, now I multiply these, I end up with 20x up top, because 4/3 and then x to the 1/3, 0 over here. And again, I'm assuming x is not equal to 0. Now I end up with this equation. Oops, sorry. Let me just recap that. So I multiplied both sides of the equation by the least common denominator, the LCD, right? And that clears out the fractions for me. That's why I did it. So this times this gave me negative 10. This times this gave me 20x. And then when I solve this equation, again, it turns out to be this nice linear equation, and I get x is equal to negative 1/2, okay? And that's all there is to it. Like I said, there are other ways to solve these equations. For example, you could have maybe started, you could have, in this case, you could have, once you found the least common denominator, you could have rewritten these as fractions that have the same denominator, and then combine them into one fraction, and then set the numerator equal to 0. That's another possibility. Another thing you can try is to solve this as a radical equation. You know, do something like write this in this form, and then you can try to, you know, reduce a little. And so for instance, here I have, if I divide both sides by 10, and then I multiply both sides by 9, I get something that looks like this. And then maybe what you can do is cube both sides of the equation, right? So you get negative 1 over x to the 4th is equal to 8 over x, which tells us that negative x is equal to 8x to the 4th, which gives us, let's see, negative 1/8 is equal to x cubed, which basically tells us x is negative 1/2.